Predictions seldom agree unanimously. But what does agreement look like between different predictions, and why does it matter? Suppose you have a lot of money on the line, and you have to decide between two predictions. They overlap a bit, but not so much that you can say that they agree. If they strongly agree, then you are willing to take the bet. If they disagree strongly, then you play it safe and fold. How do you quantify the prediction agreement? What does it look like? For this project, the predictions in question will come from fitting curves to time series data, egg prices, from the thread. In particular, using SARIMA and exponential smoothing models, we fit the time series and extract the standard deviation of their respective in-sample residuals. Using model predicted values as a mean and the extracted standard deviations, we can model the forecasts with a normal distribution. At this point, alarm bells should be ringing in your Bayesian trained head. Firstly, using in-sample residuals is too optimistic, as they benefit from forward-looking bias. Using walk-forward prediction residuals could be better to represent expectations. Secondly, assuming that the distribution of residuals is normal is unjustified and likely wrong. For example, the residuals could be heavily skewed, indicating that the model often underestimates upward changes in the data. Disregarding the matter of residuals, we proceed with the predictions they provide. These predictions are now in the form of a probability density function, a PDF, over a range of values. To get the probability of obtaining a value in a particular range, one needs only integrate the PDF over that region. Given that we now have two PDFs, one for each model, we can compare them. One way to compare is to simply plot them, which would show two normal distributions with some overlap. One can try to eyeball the distributions or make some overlap metric, but we're going to do something more general, involving entropy. First, we can convert the PDF to a probability mass function, PMF, by binning the outcome ranges and getting the probabilities for each bin with respect to the models. Using the PMFs defined on the same bins, let's call them P and Q for now, we can apply a function called the Jensen-Shannon Divergence. Depending on the base of the logarithm and some scaling, this number is between 0 and 1, where 0 means total agreement and 1 means total disagreement. Intuitively, one can think of divergence measures as answering the question, assuming distribution Q is the truth, how much change does it have to undergo to look like distribution P? I am skimming over a lot of information theory technicalities with this definition, so have a grain of salt as you digest. This JS divergence will be the metric by which we judge agreement between predictions. We now have all the pieces in place to make some visuals. You will see attached a video of a rolling window. In this window, the true realized value is shown as a black line. Accompanying the black line are colored lines representing the respective model predictions and one standard deviation confidence band. At the bottom of the plot, we see the JS divergence values. Their values are given on the right-hand y-axis. Firstly, we see that the models are largely in agreement with low JS divergence. This outcome was, however, engineered by me when I chose two models that fit the data rather well. Secondly, the overlap between the confidence bands corresponds to low JS divergence. As we would expect, the advantage of JS divergence, however, is that it will be applicable to general PMFs and not just those derived from the normal distribution. Thirdly, the JS divergence seems to spike after the data takes a sudden shock. This is likely due to the respective models adapting differently to the shocks and thus having different PMFs. As a final side note, we see that both models tend to underestimate the change in the data and tend to overshoot after the fact. In these periods, the JS divergence is often low. Thus, model agreement is shown not to correspond to model correctness. However, the models also agree often when they are both accurate. To summarize, we have fitted two models on real-time series data, extracted their predictions in the form of probability-weighted outcomes, compared agreement between predictions via JS divergence. We conclude that JS divergence is indeed a robust tool for measuring differences in predictions, albeit a bit counterintuitive to interpret. Remember, model consensus is not model correctness. The same holds true for humans, by the way. So remember to consult your local MathMerc for all things uncertain.